Welcome to a jumpstart for Pilecv4J. Pilecv4J is a video analytics and image processing library built on top of OpenCV and FFMpeg. In this video, we're going to walk through a quick example of how to use Pilecv4J, how easy it is to set up, how to extract frames from a video, and do whatever you want with them at that point. So to get started, we need to have a project. I'm partial to Maven over Gradle, so I have a real simple Maven project set up here with a simple class, empty class that doesn't really have anything yet. Note I do have a test video that's already in the temp directory that we're going to be playing and extracting the frames from and doing whatever analytics we want to do on it. This test video happens to be the opening for Dave Smith's comedy special Libertas. I picked it a while ago because it has crowds and people and cars and a bunch of things that you probably would want to do video analytics on, or at least test video analytics if you're doing object detection and face detection or person detection or crowd detection, things like that. So you could use whatever video you want, but for the purposes of this, we're going to be using that video. It doesn't really matter what video for this example, since we're just going to be opening, playing, and some minor manipulation of the video. So let's get started. The first thing we need to do is add the dependencies. So the first dependency you're going to need is libffmpeg from Pilecv4J. So we're going to add that quickly here. And since we're on Linux, x86-64, we're on a 64-bit Linux, we're also going to need the native libraries defined. And in this case, our platform is Linux x86-64. Currently there's two platforms supported, Linux x86-64 and Windows x86-64. Let's take a quick look here at the dependency hierarchy. So I explain a few things. libffmpeg from Pilecv4J, the video library which wraps FFmpeg, also includes libimage, which is the image processing library that wraps OpenCV. As we'll see in the example, all of the OpenCV Java functionality is immediately available. This does some value adds to the OpenCV library that's there, which I'll explain as we go through the example. Also, the native FFmpeg library, which contains the binaries, the .sos or .dlls on Windows for not for FFmpeg, but for the wrapper for FFmpeg. Also pulls in transitively the image processing library, which includes the wrappers for OpenCV, the native wrappers for OpenCV. In an attempt to make this easy to use, in the case of OpenCV, the entire OpenCV binary is actually pulled in a jar file. This may or may not be the case in the future, but right now it makes it really easy to use. The reason it might not be the case in the future is because if there are unresolved externals on too many different installs, it might be easier for you just to install OpenCV yourself, and then we'll just refer to it as a library, as an external dependency. But right now, this is an attempt to make it really easy to use the library. You don't even have to have OpenCV installed. And that's right here. So let's get started really quick. The first thing we're going to do is we're going to open up a stream context. A stream context is a builder that represents a media data source, so a source of media data, and processing that you want to do, a chain of processing or set of chains of processing that you want to do on that media data stream. So to start with, we're going to create a context. Now a stream context is a Java resource, and so we can manage it as a Java resource so that all the underlying native resources that are allocated, all the memory will be closed correctly, the context will be closed, everything will be cleaned up when this exits the try with resource. It's also a builder, and so we can chain the setup of our streaming context. So we need to add the source of media data. In this case, it's just going to be a file. It's going to be the file we already have out there. And we need to define the processing we're going to do. So we're going to start with a processing chain. You need to name your processing chain. It doesn't really matter what you name it. It's to distinguish, if you have multiple processing chains, to distinguish them from each other. But you open a processing chain, and when you're done defining the processing chain, you convert it back to a streaming context, the streaming context. So in a processing chain, you're usually going to do two things. You're going to select which media streams from the media source you want to use your processing on. So most media sources, MP4 files, they have multiple streams in them of different types. They'll have video streams, audio streams, subtitle streams, data streams. And so we need to select which stream we're going to do our processing on, or which set of streams we're going to do our processing on through a simple filter. There's a convenience filter, which is basically just select the first decodable video stream. And that's what this does. You can get the video stream data back in Java and do your own selection based on other criteria. But for the purposes of this example, to keep it simple, we're just going to select the first video stream. Then we want to do some processing. So we want to create a video frame processor because we want the fully decoded video frames from the one stream we selected in our Java code. And so the frame, let's be a little bit more explicit here. Frame. We get our frame back in our Java code. And so the first thing, let's just basically make this simple. We'll just count frames. And we'll just count the frames. Okay, that's it. We should be past every frame from the video in order, and all we're doing to start with is counting the frames. And we don't see any output. Well, that's because all we did was set up the builder. You actually have to play the video. Another thing to note is right now the log levels are on info, but we can turn it on trace. This actually affects the native logger also. So you can see the native logger logs to standard error. So you can see it separated from the standard out, or any other logging you might do in your own code to standard out. But there's a lot on trace, so we'll just leave it on info for now. So that's as easy as it is to get frames out of a video. I could do whatever I want with those frames now. Now a frame is an OpenCV mat. So if you're familiar with OpenCV, it's completely straightforward. So let's actually play the video and display the frames. The image processing library contains a convenience class for displaying images. Which comes with the builder, but we're just going to take the default. The default implementation of the image display is OpenCV's high GUI. The same thing if you did it from Python or if you did it from any other language and you just opened a window. We could supply a window name, so let's do that. There are other implementations, including Eclipse SWT. They're a little bit more complicated to use, so just for the purposes of this example, we're just going to use the standard default image display. So we want to actually display, I want to update the display with the frame. Now we should see the video. There you go. That was the video. Not played in real time. But if you want to play it in real time, sync it. Oops, sorry. Yeah, that should actually work. Yep. Sync it with the clock. Okay, now you might notice something strange about this video. It has a blue tint. This is because OpenCV, for some reason, standardized on BGR color format instead of RGB, like everything else does. But the underlying video library doesn't do any translation from RGB, since most video analytics libraries like PyTorch or image processing analytics typically use raw RGB images. The library puts out OpenCV mats in RGB by default. So there's a convenience method to flip these around, easily flip these around. So let's do that. So we want to display a CV mat. Now a CV mat is a Pilecv4J class that inherits from OpenCV's mat. And it adds, among other things, the ability to manage it as a Java resource. This is critical for production video applications because if you just play a video and convert each frame successively into mats, there is no resource management. And so the Java finalizer is used in the mat to clean up the underlying native memory that stores the frame data. So if you're processing a video and you're pulling a frame every 40th of a second, every 60th of a second, every 30th of a second, however frames per second you're doing, then you are going to quickly run out of memory because the Java garbage collector does not track off-heap native memory. So in order to do this, we add, Pilecv4J adds a mats as resources. So we can take the frame and we can just say, give it to me as BGR. Now, we can also tell it whether or not we want to guarantee a deep copy. If it turns out the frame is already in BGR, it won't do a deep copy if you supply false. If you want a deep copy no matter what, because you're going to use the frame for outside of the context of this callback, then you can pass true to it and it'll actually make a copy of the frame for you to use. Okay, so we want to display the BGR version of this. So here we go, color corrected, playing the video. Notice the cabs are yellow now instead of blue, so it's working. So you can do whatever you want with these frames. So for example, like I said, a frame is a mat, so we could, let's say we wanted to flip it. This is OpenCV Java API. And we'll flip it around on the x-axis. So here we go, real simple example of just flipping the video upside down. We can also open another processing chain. So let's do that quickly here. We will open a second processing chain. We'll call it second. And we'll go back to having the first one not flip it. Let's add a second display. And let's write to the second display here. So now we have two processing chains. So here you go. You have one of them upside down and one of them right side up. So this is not very efficient because what's actually happening here with each processing chain is you're running the decoder twice. So the processing chain does the stream selection at the base packet level, and then the frame processor will decode the frame using whatever the decoder is for that particular stream that's been selected and pass the frame to Java for you to do what you want. In this case, flip it upside down or display it or whatever you want to do. So we could make this a little bit more efficient by, and well, actually we don't necessarily want to do the frame count twice. We can make this a little bit more efficient by decoding it only once, by not opening the second processing chain, decoding it once, but displaying it twice. Oop. We're affecting the first display by doing this. So let's create a flipped CV map. Again, remember CV mats are mats, OpenCV mats with resource management, as Java resources. Now we will flip, and we will display flipped. Okay. That's it for the first quick start, the first simple example. If you have any comments, let me know. If you have any suggestions for the library, let me know. There's going to be links in the description to the project. Submit any issues you find. I greatly appreciate it. Any feedback would be welcome. Thanks.